Hello everyone, this is Saria Mghamis and I'm here today to present to you the work done together with my colleagues at the University of Lincoln in UK and the University of Padova in Italy around the topic of enhancing human motion prediction leveraging a neuro-symbolic approach. The aim of our work is to build a safer autonomous navigation system leveraging an enhanced model for human motion prediction. Our aim can have substantial impact on application domains such as logistics, transportation, and warehouse, as the EU project DARCO, supporting this work and dealing with efficient automated logistic operations. Though we can find in the literature many advanced architectures for human motion prediction with a good performance, all these architectures embed the dynamic as the nearby humans and or static context as the shelves and the conveyor with equal weightage. This equal weightage is not the real case though, as the influence of each single neighbor on the target person varies depending on different interaction variables or factors. Among those interaction variables is the relative position of the target and each single neighbor. In our work, we embed the relative position in a qualitative representation as it is more intuitive for reasoning on multi-agent interactions. In addition, we propose the likelihood of the next qualitative interaction state at time t+1, given the current interaction state, to be the factor weighting the effect of the neighbor interaction state on the target position. Looking back on the literature of context-aware human motion prediction, we can distinguish between works considering dynamic context only, static context only, or dynamic and static context together. We narrow down the background to the works embedding at least the dynamic context, as it is crucial to the study of public and social scenes where crowd may arise. To start with, we will brief on two main baselines for context-aware human motion prediction, and those are the social LSTM and the social GAN, generative adversarial network. The social LSTM gives consideration to the dynamic context only. It leverages a social pooling mechanism, pooling the hidden states of the neighbors, and whose position is embedded in an LSTM layer. The social GAN, the one on the top right, gives also consideration to the dynamic context only. It leverages a pooling mechanism, which, on the contrary of the social LSTM, embeds all people in the frame of view and pulls the hidden state of the target person with the embedded relative position of neighbors in the encoder of a generator module. Other works incorporating both dynamic and static context are the desire architecture on the left and the peeking into the future work on the right. The desire architecture needs both the observed and future trajectories as input during training. It encodes both trajectories in two separate conditional variation autoencoder-based RNNs, and then it generates, at the second stage, sample predictions. Those sample predictions are then refined at the third stage through an iterative feedback of the prediction error at the decoder input, and they got ranked by a reward score at the output of an RNN-based decoder. Feature maps of the semantic scenes are also input at the decoder level. The peeking into the future work solves two problems in one architecture. It tackles the problem of human motion prediction and the activity prediction. It embeds the static context as features extracted from the semantic scene, this block here. In parallel, it embeds the target person behavior through key point and appearance encoding, extracted from a CNN network. In addition, it encodes the geometric relation between the target and every other object in the scene. This every other object can be dynamic object like a car or mobile object like a box, moving object like a box, or another agent or person in the scene. On another side of our work lies the aspect of modeling multi-agent interactions, whether human-human or human-robot or human-object. In that direction, we can find works dealing with one-to-one modeling or crowd modeling. We will briefly focus on the area of one-to-one modeling as it reflects better the individual effect of the neighbor agent on the target motion. Hence, we can distinguish between quantitative modeling or qualitative modeling. The qualitative approach for modeling interactions has been proposed as an intuitive way for interaction description. In the top figures, in the top right and top left figures, those works deal with qualitative representation of interactions between agents. The work on the left of Dondran Bayal, in that work, the authors constructed a conceptual neighborhood diagram denoted CND from observational data of interactions between human and robot collected from an experimental setup. The CND diagram illustrates the possible transitional states from each possible state spanning the 2D space. Our current work deals with multi-agent interactions representation to embed it in the target motion prediction model. We leverage on the qualitative representation of spatial interactions as it is an intuitive approach for reasoning and description. We advance on the state-of-the-art in context-aware human motion prediction by narrowing down the work on the dynamic context effect and keeping the static context embodiment to our future work. Our approach proposes to weight unequally the interactions embedding by leveraging on the notion of the likelihood of the future qualitative spatial interactions. For that, we use the qualitative, the first point here, we use the qualitative trajectory calculus denoted QTC to represent qualitatively the spatial interactions. We then, second point, construct the CND of all possible transitional qualitative states in order to estimate the likelihood of the future state. The likelihood estimation will represent the labels of the qualitative interactions, which serve the symbolic knowledge input to a neural layer. Regarding the first point, which I just addressed, which is the QTC representation of interactions, a QTC was presented in the literature under different types, among which is the cross type denoted by QTC with a subscript C. We can distinguish between two types of QTCC, which are QTCC1 with 4 symbols from Q1 to Q4, and the QTCC2 with 6 symbols from Q1 to Q6. And each single symbol will belong to a discrete set of dimension 3. For simplicity, we take advantage in this current work on QTC with a subscript C1, where Q1 and Q2 represent the moving towards away dichotomy between two agents. Q3, Q4 represent the left and right dichotomy. Q5 in QTC-C2 will represent the relative velocity between two agents, while Q6 symbol represents the relative angle between them. For example, in the right figure, the Q1 and Q2 here will have the symbol plus or +1 for numerical reasons if both body points PK and PL are moving towards each other, and they will have 0 symbols if they are still. Regarding the second race point on constructing the CND for QTC C1, the CND for QTC C1 has a very complex illustration as the space includes 81 possible states in total. We illustrate here on the right-hand side a subgraph of the CND corresponding to the possible transitional states of only one state, which is minus, 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 the central node. In general, each state cannot transition to all other 80 states. Some rules apply. For example, one of the rules, the plus and minus symbols cannot transition directly to another plus and minus symbol without passing through the 0 state. This state here, minus, 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 will have 15 possible transitional states in total. Said this, we label the transition between a pair of QTCs with alpha CND, with alpha being the likelihood of the next transitional state given the current one, And this alpha is equal to the 1 over big N with a subscript TR, which is the total number of transitional states given the current QTC at time t. Though the symbolic approach can be applied to any neural-only architecture for human motion prediction, in the experimental setup of this paper, we tested the approach on two baselines from the literature. The first baseline is the ASGAN architecture, which deals with dynamic-only context and shows outperformance in terms of accuracy and time complexity. We present a new version of ASGAN pooling mechanism, so we acted on the pooling mechanism to enhance it, where we concatenated the hidden states of each agent, represented by the green box and the blue box. We concatenate those hidden states of each agent in the scene with another vector, this one here and this one here, which represent the weighted embedded relative position of that agent with its neighbors. And those weights are loaded from a dictionary and exploit the CND diagram. We tested the new ASGAN version with the new pooling mechanism on public 5 datasets with pedestrians, like the university scene and the Zara scene dataset. The dataset was collected from top-down fixed camera and stereo rig mounted on a car. After training and testing the new Neuro-Symbolic ASGAN architecture, we extracted the ADE and the FDE matrix. Those are the average displacement error and the final displacement error. And those matrices serve for quantitative evaluation. The table here shows that the Neuro-ASGAN, the third row here, has an ADE mean relative gain of 60% and 78% for the 3.2 second and 4.8 second time horizons respectively, and the FDE mean relative gain for Neuro-ASGAN is 58% and 76% for the 3.2 seconds and 4.8 seconds respectively time horizons, with a peak performance of Neuro-ASGAN on the Zara 1 dataset. With a relative gain of 70% and 85% when ADE was evaluated. For a qualitative comparison, we plot the predicted trajectories of one batch on the test set for Zara 1 dataset, considering only 6 pedestrians for the purpose of clarity. So we see here only 6 pedestrians in each graph. We specifically highlight the pedestrian in blue, whose predicted trajectory with Neuro-ASGAN, this one here, is closer to the ground truth, which is here, than the one predicted with the original ASGAN architecture, the one in the middle here. In addition, we tested the NeuroSym approach on social scenes as the Jackrabbit dataset, collected from the social robot point of view in dense and social scenarios. Jackrabbit was never deployed for human motion prediction application. Hence, we choose the dual attention recurrent neural network, DARNN architecture, from the state-of-the-art to test the NeuroSym approach on Jackrabbit dataset, collected from a 360 Velodyne LiDAR and fisheye camera as mobile sensors. The DARNN is a generic architecture for time series forecasting. It benefits from a multivariate data input, an input and a temporal attention, an input, the first block, and a temporal attention mechanism, the second block. It showed better performance in terms of accuracy for generic time series forecasting and allows to incorporate static object as any other moving body point. To integrate the symbolic knowledge on interactions in DARNN, we input the likelihood labels in the CND layer in orange. So this layer is input or is incorporated in the input attention mechanism directly after the input attention layer and just before the softmax layer. And this is with a multiplication operator. Another stage of our study is the Jackrabbit processing dataset for input and output data generation to the network. The crowded scenes of Jackrabbit can represent a computational complexity to the network input size if they are left unbounded. Hence, we follow a clustering technique by generating clusters of radius equal to the social distance taken from the literature on proxemics. And those clusters are generated around each agent. Each cluster is now input to the network, where the first time series is the one of the centered person, and the remaining time series are the neighbors in the cluster. The output of the network is the predicted time series of the centered person. We conducted experiments on the cafe scene from the Jackrabbit dataset, and the quantitative results show a 22% relative gain of the Neuro-Sim approach over the 3.2 seconds time horizon, and on the root mean square error metric, while it shows a small loss of performance over the 4.8 second time horizon with a 4% loss with respect to the original architecture. Our approach, our current work is dealing with a new version of ASGAN, incorporating the causality of the observed motion into the Neuro-Sim architecture for enhancing human motion prediction further. Also, we plan on integrating the Neuro-Sim architecture in an autonomous navigation system. Last but not least, the code is released in an open source repository, which you can find under GitHub by scanning the QR code. We thank you for your attention and we welcome any discussion around the topic.